some step 2 curve sketching then, question 1 and 2 from the booklet that is in the Millennium Maths Project to do. We'll start with this question, obviously. Determine the nature, so sketch this and everything. So, okay, we've got a lot to do here. Firstly, we'll assess extreme points, we'll find the y-intercept, and we'll find the roots. That'll be the first thing to do. I've gone way overboard in finding a y-intercept here, haven't I? Clearly, the y-intercept is at 0 when you put an x at 0. And when x is very large, this is just a positive x to the power 6 polynomial, so we're going to have extreme values up here and up here. So that's all good. And the roots when y is 0, clearly, because it's already nicely in factorized form, roots at 0, -1, and 2. So that's all good to go as well. So we'll put those down, and my sketch is taking shape. I do need the coordinates of the stationary points, and that's going to be the most tricky bit about this, or at least the most long-winded part of it. We're going to need to differentiate this. Now, we could expand that whole thing out and then differentiate it. It's actually much easier to, and if you haven't seen this before, product rule works for 3 things. It works for 2 things, of course, like this, but it also works for 3 things, where you just differentiate 1 each time and leave the other 2 alone as you go along. So yeah, lots of color here, which is nice. So differentiate x for a 1, leave the other 2 alone. Differentiate this for a 1, leave the other 2 alone. Differentiate this for a 4, x minus 2 to the 3, and leave the other 2 alone. It tidies up to be this, which will of course then set to be 0. I can also factorize out x minus 2 to the power 3 as soon as I see it in all those terms. It's going to make everything much easier for me, because now I can expand out this, which is really just a quadratic when it comes to it. And I don't have a problem with expanding out things that will make a quadratic, because I know I can just refactorize them again later. Of course, dy by dx needs to be 0 for stationary points. So okay, that's fine. X equals 2 is clearly a solution. And the other one is from here, this equaling 0, that factorizes, which is nice of it. And we get solutions of -2/3 and a half as our other 2 solutions. Now, we need to know the coordinates of these stationary points, not just where they are roughly. So I need to put in x is 2, x is -2/3, and x is a half into this original equation here. Now, the thing is, I actually don't need to do that for 2, because x equals 2 was already a point that we know happens at 0. So that's great. So that's already done. So we don't need to do that again. But x equals -2/3 and x equals a half, I do have to put in here. I can be quite lazy about this, I think. So putting in x is -2/3, we're going to get this. I can just tidy up the brackets a little bit, and then I can say 8 is 2 to the 3, and then say on the top here I've got 2 to the 12 times 2 is 2 to the 13. On the bottom I have 3 to the 4 times 3 times 3 is 3 to the 6. And it's going to be this. They don't expect you to actually do any more than that. They're just going to say it's there. It's a negative number. So when x is -2/3, which is in between 0 and -1, we're down here somewhere, and our stationary point would be down there. And now for x equals a half, same kind of deal. I'm just going to put a half in, just going to tidy it up as best as I can. So 3 to the 5 on top and 2 to the 6 on bottom, it looks like. And that's a positive number. So we're just going to put it somewhere up here. And this is a continuous curve, of course. So I don't need to assess the maximum or minimums of those, or whether they're maximum or minimums. I can just see, because it's a continuous curve, it's going to come down like this, up like this, down like this, up like this, and that'll be all good to go. It's a polynomial, right? It doesn't do stuff like this. It just looks like this. And that's GeoGebra's drawing. They just expect you to put a curve through these things like this, and you'd be fine to go. Okay, cool. So from there, it's asking us to sketch this curve. Now, it hasn't asked us for anything specific. It's just asked us to sketch it. So I don't need to give all the exact places and all of the where the stationary points are now going to be or anything like that. Just need to sketch it. So okay, we're going to use this sketch. All that's happened is that y has turned into a y squared. I've made a video about sketching functions of the form y squared equals f of x. You can probably find it on the channel somewhere if you try. But basically, only 2 things happen. Firstly, for any x input where your function is negative, like here, for example, x equals -0.5 gives us -10, that doesn't exist anymore, because you're going to get y squared equals -10 when you put in that same, because it's the same function here, right? Put in -0.5, you get the same result out. Y squared equals -10. That's not a thing. So basically, any place on the original function where y was negative is just not going to exist anymore, which is this whole tree down there. That's just not going to exist anymore. It's just going to go away. Now for the positive places, so like if you put in x as 1, you get 2 out. So okay, you put in x as 1, you get 2, so you get y squared equals 2, but that means y is plus or minus √2. So of course, √2 is slightly less than 2, so the graph is going to squash down, but also be reflected by itself and have 2 versions of itself above and below because of the plus minus that you'll always get. So that's the second rule, is that any positive place is reflected. And so it's going to squash down a little bit, but also be reflected here. and then this is going to squash down, but also be reflected here. And then this over here, remember, don't forget this bit, is also going to be squashed down, whatever that means, and then reflected down here. And you end up with this kind of sketch here. Again, anything that looks roughly like that will be good enough for the marks there. And I don't know why I just chose to put them close to each other. I guess there's some quite nice stuff going on here. I mentioned that it squashes down when you take the square root, except if you're underneath 1, of course, when you square root number less than 1, between 0 and 1, it actually gets bigger, right? The square root of 0.5 is like 0.7-ish. So the graph doesn't always squash down. It can actually stretch back up again. But yes, that's just a slightly finer point. So the last bit then is what happens if instead of making this a y squared, you make all of these x squareds. And now something important happens here, which is that if you imagine putting in x is -1 into this, you square -1 every time, which makes +1, and it's the same as if you were just putting x as 1. So whatever x was 1 was doing is what x is -1 will now be doing. And likewise, for any value of x, if you put in the negative, that will be the same as if you put in the positive of that value, because when you square them, the negatives just become whatever the positives did squared. So putting in 5 into this will be the same as putting in -5. So long story short, this graph is simply symmetric around the y-axis, because all of the positive inputs will give you the same thing as the negative inputs do, and vice versa. And it's an even function, which means reflected around the y-axis. There's also some other stuff going on, in which case it sort of stretches and squashes outwards. But remember, this is just a sketch. So all we need to do is sort of vaguely draw this shape on both sides of the graph. This is GeoGebra's excellent drawing of it. But all we had to do was draw this shape on both sides of the axis, and just make sure it's a nice even function, and we get full marks. So question 2 then is about a cubic curve with maximum PM and minimum QN, and so on. So it's a cubic. It clearly goes through the origin, because when x is 0, y is 0, and P is bigger than 0, so it's got a maximum point over here somewhere. And N, so its minimum point is still above the axis. N bigger than 0 means its y value bigger than 0. So the cubic must look a bit like this, something like that. Let R be the origin enclosed by this, x equals P. So x equals P is a vertical line here, and y equals N is a horizontal line here. So I think it looks a bit like this. And that's the area enclosed. Except it could also be this area as well, I guess, because that's enclosed by the curve, this line and this line as well. And I think they just made a mistake in the exam. In fact, the mark scheme says they did, where they just didn't realize people might work out this area. They intend for you to work out this area here, or at least for now, think about this green area here. So we'll think about this green area here as we go through this question. So that's the setup. Express B and C in terms of P and Q. Now, P and Q are about the maximum and minimum points on this graph, so very logical to differentiate this, I think. So let's differentiate it and set it to 0. That makes this. Set it to 0. Now, we know that the solutions to this equation here are, of course, where the stationary points are. But we know the answers to that are P and Q, because we've been told that. So therefore, we could write this as, in factorized form, x minus P, x minus Q. Except we can't quite, because this 6x squared messes up. So let's just throw a 6 in here, and then we're fine. And now we can just compare coefficients. Right, the C must be equal to minus Q times minus P times 6. So therefore, C is 6QP. And then once you put that in, replace that with 6QP, you can just compare the x values, right? So here you can have minus QX minus PX times 6 equals minus 2B. So therefore we get this, and we'll get B as that. So that'll be B and C in terms of Q and P. So that's all done as well. And we can also use those values. We can put them into our curve. So this is just me putting B there and C there. So that's all good to go from the original expression that they gave me. So that's all good. Fantastic. Mark and sketch the point of inflection. Now, I've got an entire video on this channel where I talk about inflection points because they're really interesting, and I would highly suggest that you go watch it. Essentially, you might look at this and go, oh, well, there's no point inflection, right? Point inflections do this kind of business, and they sort of have gradient 0 and go up and then up again. That's not necessarily what a point inflection is. A point inflection, the rule you can just state, I guess, is that d2y needs to be 0, but dy by dx doesn't have to be. So you don't have to have a point inflection on a flat point. And in fact, there is going to be a point inflection right here, halfway between the two turning points, and I'll prove it. Let's find dy by dx. We don't care about this. There's no condition that needs to be met here. Let's just find d2y by dx squared, which is this, and set that to be 0, which is the condition that we need to meet. And yeah, let's just obviously solve this for x, move that over, divide by 2, or divide by 6, actually, and then divide by 2, and yeah, perfect. X is the mean of Q and P. It's right in the middle of Q and P, so it must be roughly here somewhere. In the video, I talk about how inflection points, a really nice little definition of them is a point where you have local rotational symmetry. In fact, if you bang this curve in GeoGebra and then put the inflection point down, there's a little tool you can use where you rotate the graph around itself, and you'll see that it perfectly matches up with itself every time you rotate it around, which is really cool. But anyway, that's our point of inflection, so we're all good to go. We just need to mark up the point, and we've done that, so that's fine. So all that's done. So now we need to show m minus n is this. Now m and n refer to the y-coordinates at the stationary points. So therefore, let's just put in p and m into here to find an expression for m, and p and n and q into here to find an expression for n. And now let's just do what they have asked us to do, m minus n. So let's do m minus n. Let's take those two things away. It's a little bit annoying and tricky, but lots of things cancel, lots of things group together. We get this. If you write this in a slightly different order, which is to say this, hopefully you'll see that this is very nice. It's just q minus p, or cubed, I believe, because, yeah, it's just following some nice little 1, 3, 3, 1 business, and all going very well. So that's all great. Good. So that's that part done as well. And now we'll get to the last part, which is show the area of R is this guy here. Now, there's the easy way to do this, and there's the hard way to do this. I'm going to start with the hard way. The hard way is, of course, to do some integration, to say that the region R is the integral of this curve, which we've got here, between Q and P, right? Like this. Except it's not quite, because that integral there would find you all the area beneath the curve. In other words, it would include this box underneath that I don't want. So what I'm going to do is I'm going to think, well, what's the area of that box? Well, it's height n, width q minus p, I think. So therefore, if I simply take away n times q minus p from this integral, then I will actually end up with the proper area that I want up here. So that's exactly what I'm going to do. I'm going to integrate this, and I'm going to take away this box afterwards. So let's do the integration first. So yeah, integrate every term with respect to x. Then let's throw in q and p into there, which gives me this. Let's try and simplify this as much as possible. I'm just doing boring algebra here, so you don't need to worry about it too much. I'm just cancelling a lot of terms, putting things together. I get down to here. Now, at this point, I'm not allowed to have an n here, because everything else has q's and p's, so I'm hoping that'll cancel down to this. But n, of course, is just what happens when you put q into this expression here. So and we said that earlier, didn't we? So now I can put all of this in for the n business. You can see why I said this is the hard way of doing it. Expand out some more algebra. It's all super boring. I'm just doing a ton of expanding and collecting and being very careful as I do so. There might have been some more intelligent factorizing you could do early to get all this to go away. But in any case, eventually you end up here, and this looks great because if you just rearrange the terms or rewrite them and take out a factor of a half, you can see this looks perfect. 1, 4, 6, 4, 1. With the minuses in the right place, this is just q minus p all to the power 4, which is fantastic. So we're all done. Now, the easy way of doing that question is not to do any of that. The easy way to do it is to use the things that they got you. Step questions don't just ask you to randomly find the point of inflection and then randomly find, this whole, where was it, m minus n equals q minus p to the power 3 business. Like, they don't just ask you to do that randomly, only to then ask you to do an integral that's horrendous. Like, that's not how STEP works. What they were trying to do is point you in a much easier direction as to how to do this question without going through that effort. Because, as I said before, points of inflection are points where you have local rotational symmetry. So in other words, if you jam a big box around this shape here, roughly here, this curve is symmetrical around this point I, which means that these two areas are equal either side of the curve because of this symmetry here. So to find this region R, I can just work out the area of the box and halve it. And you can see where this is going to be helpful now. This distance here is q minus p, as we already said. This distance here is m minus n. But we already said m minus n is q minus p cubed. So therefore, the area of this box is q minus p times q minus p cubed, which is q minus p to the 4. And then we just halve it to get our R, because it's half of the box, and we end up here immediately. So yeah, really nice little question. I love that they did that and probably forced lots of people to do all the horrible maths that I did, only for some people to do this and earn the marks in 3 minutes. So yeah, great, really lovely.